Before engineers build, before scientists experiment, someone must first decide how every piece should fit together. Classical computers also follow blueprints. Logic gates are connected together, guiding bits through a sequence of carefully planned operations. But quantum computers need a very different kind of blueprint, one designed not for bits but for qubits. These blueprints are called quantum circuits. They tell quantum computers exactly how qubits should evolve over time. Each horizontal line represents a qubit. Unlike electrical wires, they don't carry current. They track the changing state of quantum information. In quantum circuits, time flows from left to right. Every gate placed along a wire changes the qubit's state as computation progresses, like instructions in a recipe. Each one performs a specific operation on one or more qubits. Some gates, like the Hadamard gate, create superpositions, allowing qubits to explore many possibilities simultaneously. Others, such as phase gates, alter hidden phases, influencing how quantum waves interfere later in the computation. Multi-qubit gates like CNOT can entangle qubits, creating correlations impossible in classical systems. More advanced gates, such as Pauli-Y, allow computations to depend on multiple conditions simultaneously. By combining just a few gates, we can already construct surprisingly powerful quantum circuit states, where two qubits become deeply entangled. Eventually, measurements convert fragile quantum states into ordinary bits that we can observe and record. A quantum circuit is much like a cooking recipe. Qubits are the ingredients and gates describe the sequence of steps. Changing the order of gates often changes the result entirely. In quantum mechanics, sequence matters. Some operations can happen at the same time, allowing quantum computers to process information efficiently. Scientists measure complexity using circuit depth, the number of sequential layers needed to complete a computation, sensitive to noise. Longer circuits increase the risk of errors. Engineers therefore optimize these complex circuits to maintain performance, reducing unnecessary operations to improve reliability. Some circuits can even teleport quantum information from one location to another. Others enable algorithms capable of factoring enormous numbers, much faster than known classical methods. Quantum circuits can also search enormous spaces of possibilities, more efficiently than traditional computers. Every gate drawn in a circuit eventually becomes a precisely engineered pulse. Today, quantum circuits have become a universal language, helping scientists communicate and design increasingly complex quantum systems. What begins as a few simple gates can eventually grow into computations beyond the reach of the world's most powerful supercomputers. Every quantum breakthrough begins with a simple idea: arrange the right gates in the right order at the right time. From teleportation to cryptography, the extraordinary abilities of quantum computers emerge from these elegant blueprints. Quantum circuits are not machines themselves. They are instructions for possibility, teaching matter how to compute in ways that nature has quietly understood all along. Carefully engineered pulse. These pulses move inside a machine operating only fractions of a degree above absolute zero. Like a symphony, quantum algorithms arise from combining a small collection of gates in sophisticated ways. Researchers are already designing circuits to solve problems beyond the most powerful supercomputers. Quantum circuits have become a universal language for exploring entirely new forms of computation. The blueprint was never just symbols, it was a map, showing qubits how to move and interact. It is a map designed to ultimately reveal answers hidden deep within the quantum world. Right instructions can teach matter to compute, opening doors to possibilities we are only beginning to imagine.